Okay, this is segment 2 of our Unit 6 naming unit, lecture number 2. Today's topic is ionic compounds and how we name those ionic compounds. So we're going to dive right into those guys. First thing we want to talk about is for an ionic compound, we need to identify how do we know we have an ionic compound versus a molecule, organic, or an acid. So the key thing you look for is, do you have a metal? If you have a metal present, you know that you're dealing with an ionic compound. Okay. Another way of looking at that is, do you have a cation bonded with an anion? Okay. You're always going to have a metal written first, and then it's going to be followed by either one or more nonmetals as you deal with our ionic compounds. Recall there is a transfer of electrons there. Now, because we are transferring electrons from one atom to the next to create ions, unlike molecules where we have multiple different ratios that we can perform, for ionic compounds, the ratio always has to be the same. So when I bond sodium with chlorine, I have to have a 1-to-1 ratio. When I bond magnesium to chlorine, it's a 1-to-2 ratio. So for each one of our different compounds, we have to have these different ratios. Now because of that, because we only have one possible ratio, there's no reason to use a prefix. So when I say sodium chloride, for example, I have sodium and I have chlorine. Sodium's charge is a 1 plus, chlorine's charge is a 1 minus. So every time sodium combines with chlorine, they're going to do so in a 1-to-1 ratio to make sodium chloride. However, if I had magnesium chloride, magnesium's a 2 plus, chlorine's still a 1 minus, this ratio would have to be as such, 1 magnesium, 2 chlorines. There is no possible way of getting anything besides a 1-to-2 ratio here. So magnesium chloride, we don't use prefixes with that because this is the only possible way that magnesium combines with chlorine. Now, because we don't have prefixes, we have to be very careful about our charges and know what the charges are as we go through ionic compounds. So our first step is, how do we determine that ratio? Okay, and again, we fall back to what are our different ionic charges that each atom is going to generate when they turn into ions. So for our main group elements, if we recall, our main groups are groups 1 and 2, and then we skip 3 through 12, and then we get 13, 14, 15, 16, and 17. So we know that our group 1 is always a 1 plus. Our group 2 is always a 2 plus. We skip these. Group 13, really the only element we know in group 13 is aluminum, and that's a 3 plus. Everything else we don't know. 14, we never really talked about in terms of charges, so we ignore that one. 15 is a 3 minus, 16 is a 3 plus, 16 is a 2 plus, 2 minus, 16 is a 2 minus, and 17 is a 1 minus. So these are the standardized charges that we set up in previous units. Just recall those, they should be on your periodic tables. Okay. Now, for the groups that we skipped, in the middle, so groups 3 through 12, also known as our transition metals, and then any metals under the stair-step line, we have to deal with those a little bit differently because we don't know their charges. So when we work with these metals, the transition metals and metals under the stair-step, by writing out the compound, we wouldn't know their charge. So instead, we have to use something in the naming system to identify that charge. Okay? So as you're working with these, things to remember. Identify the charge on your anions and your cations. Groups 1 and 2 will be metals. Groups 15, 16, 17 would be nonmetals. And then there are 3 that we had to memorize in our system: aluminum, zinc, and silver. Zinc and silver are part of our transition metals. Aluminum is that one that's sitting under that stair-step line. We should remember that their charge for aluminum is always a 3 plus, zinc is always a 2 plus, and silver is always a 1 plus. If we remember that, we can use that in our naming system. Okay. So let's go on to how do we actually go through this process of naming these. So we're going to focus on the cations under the stair step and those other transition metals. When we're working with these, first thing we need to realize is that when we have things like copper can form more than one charge. It can form a 2 plus charge or a 1 plus charge. Because it has more than one possibility, somehow we had to tell the world what copper we're talking about. Okay? So when copper forms a 2 plus, we will follow that with a Roman numeral 2 in the word format or the name format. And when copper is a 1 plus, we follow that with a 1. Okay? So for example, when we're working with sodium, sodium always is Na plus. So we just call it sodium. We don't ever give it any other name besides sodium. But because copper is a 2 plus or 1 plus, we call it copper 2 or copper 1. Notice how sodium doesn't have the Roman numeral behind it, but these two do because they have more than one possibility. Sodium only has one possibility, so we don't use a Roman numeral behind it. Okay. Now, one thing that most kids or we see as a misconception as we get into the naming system is they think the Roman numerals tell you how many are there. So copper 2 doesn't mean you have 2 coppers. It means the charge is a 2 plus. So this Roman numeral is for the charge. It's for the charge. Okay. Let's take a look at our two compounds down here. We have FeO and Fe2O3. Okay. Now, if we go to name these, say what are these things called? Well, Fe is iron, so we get iron. So we get iron. And then oxygen, we call that oxide. We change that ending from oxygen to oxide. So we go from iron, oxide. Okay? Here's a problem. If this is iron oxide, and this is iron oxide, how do we know which one we're working with? And we really don't. So we had to have a better system in place to identify which one is which. And it actually makes a pretty big difference because this stuff here is a protectant. Okay? So iron oxide like this actually protects metal from rusting. This is rust. So we go from this being something that stops rust from happening to the rust itself, just by the ratio that we have. So we had to be able to name that properly so when we talk about iron oxide, we know which one we're dealing with. Okay? So just saying iron oxide is not enough. A better way of doing that is use that Roman numeral with your word of the iron. So for FeO, we would call it iron 2 oxide because the charge on the iron would be a 2. Fe2O3, we call it iron 3 oxide. Now you might be asking, well, how do I know what the charge is? Because it doesn't tell me the charge in the formula. Right? Nowhere up here did I write down the charges, so how do I know that that was iron 2 versus iron 3? Well, again, we go back to our ratios here. So it's oxygen is a 1 ratio, and iron also is a 1 here. We have 1 oxygen to 1 iron. Okay? Again, we don't know iron's charge, but we do know oxygen's charge. Oxygen's charge is a 2 minus. And if you have a 2 minus, and it takes one of these to balance out one of these, 2 minus, we have one of those, so the total negative charge is a negative 2, which means the total positive charge has to be a plus 2. Well, the total positive charge has to be distributed over just 1 iron, so the iron has to be a 2 plus. So now that we know this, we can say that this is iron 2 oxide. Do the same thing down here. the oxygen still is a 2 minus, but now it takes 3 of those oxygens to balance out 2 irons. So we have a negative 2 times 3. We have a total negative charge of negative 6, which means we need a total positive charge of plus 6 because this compound has to be neutral. They have to equal 0 if you add them together. So if I have a total positive charge of 6 and it takes 2 irons to get that, each iron has to contribute a 3 plus to that. So it's a 3 times 2 is 6, 2 times 3 is 6. So we have a plus 3, we have a minus 2. In this case, now that we know this is a plus 3, we call this iron 3 oxide. Okay. In the naming system, notice how we are not capitalizing anything. These are not proper nouns, so we do not capitalize those. Okay. Now, don't forget, for aluminum, zinc, and silver, aluminum is always a 3 plus, zinc is always a 2 plus, and silver is always a 1 plus. So we will not be using Roman numerals with those 3 metals. Okay. As we go through the process of naming these compounds, we call them binary ionic because we're only dealing with 2 different atoms at any one time. So, as we're working through it, let's go through the process. First thing, naming the cation or naming the metal. When we name the metal or we name the cation, you just use the original word of the atom for the cation. So Na plus is sodium. Fe2 plus is iron 2. Okay, we need the 2 here because iron has more than one possible charge. Sodium, you would not put a 1 behind it. It's not allowed. You cannot do it. It's wrong if you do because sodium only forms a 1 plus. So we only use Roman numerals when there's more than one possibility. Aluminum is a 3 plus. We just call it aluminum, only possibility. Iron, again, has more than one possibility, so this is a 3 plus. We call it iron 3. Now, for simple anions, your nonmetal, what we do is we change the word from chlorine to chloride, from oxygen to oxide. So we basically change our ending. The IDE ending tells us that we have a simple anion. So oxide tells us we have oxygen. Chloride tells us we have chlorine. Okay. Usually you drop off the last syllable. The only exceptions to that is that I can recall off the top of my head is oxygen. We don't say oxygen or oxide. It's oxide. And then phosphorus. Phosphorus, we drop off the last 2 syllables, or us. So phosphorus becomes phosphide, okay, on those 2 things. Now, you put them together, and you get the name of the compound. So NaCl would be sodium chloride. FeCl2 would be iron chloride, but now we have to decide which iron are we working with again. So we have iron with chlorine, so we drop off the chlorine, we change to chloride, and we need to decide what goes in here. Is it iron 2 or is it iron 3? Well, let's take a look. We have, for this example, FeCl2, so it takes 2 chlorines, each one's a 1 minus, which means your iron has to be a 2 plus to make this a neutral compound. So this is iron 2 chloride. Go down to FeO, same idea. Which iron are we dealing with? Well, FeO is 1 of each. That's a 2 minus, so this has to be a 2 plus. So that would be iron 2 oxide. And then we go down to this one, and we have aluminum with chlorine. Aluminum doesn't need a Roman numeral, so we just say aluminum chloride as such. Okay? If we go across and we see we have sodium with oxygen, we would call this sodium oxide. And we have iron, and now our ratio is a 1 to 3, so it's iron 3 chloride. Here we have iron 3 oxide, and then again aluminum oxide. So as you go through the process of naming these, the biggest thing to think of first of all is, do I have an ionic compound? Well, it starts with a metal, so yes you do. Name it by the rules for ionic compounds. Second thing you ask yourself is, does my metal have more than one possible charge? Okay, most metals do. So all the transition metals and all the metals under the stair-step line do. The only metals that don't are the group 1, group 2, aluminum, zinc, and silver. So really, most of the time, you're going to be putting these Roman numerals in. If you happen to have a group 1 metal, like sodium, or aluminum that only has one possible charge, you just omit the Roman numeral. So what I would do is start off by assuming you'll use a Roman numeral, and then if you don't need it, just get rid of it or don't use it. Okay? Now, when working with the formulas for binary ionic compounds, we need to have a neutral compound. So again, we've been doing a couple of these already, but let's just kind of go through the last part of this. For example, if you have magnesium nitride, I say write this formula. Well, magnesium we know is Mg. Nitride was basically nitrogen, but shortened down for the "ide" ending to indicate a compound. So magnesium nitride. We know the charge on each one of these ions. Magnesium is a 2+, nitrogen or nitride is a 3-. These must be neutral. Okay? Right now they're not. It's a 2-to-3 ratio. So what we need to do is use subscripts to change that ratio to give us the right amount of each substance. So what I always say is, what's your least common multiple between 2 and 3? Well, that happens to be 6. So 3 times what gives you 6? Well, that would be 2. 2 times what gives you 6? That would be 3. So we end up getting Mg3N2. Now, when you write your formula, the last thing you want to do is you want to rewrite this without the charges written in, because the charges aren't really part of the formula. So we would call this Mg3N2. That would be magnesium nitride. Okay? There's no other possible ratio. It has to be a 3-to-2 because of the charges that they have.